Thank you for the introduction, and thank you everyone for coming. This is some work I did with Antoine Kaufman at MPI and others at UT and University of Washington. I'm happy to talk to you about it today. I'd like to start off by talking about remote procedure calls in the data center environment. RPCs are a common building block for many data center applications. Let's say, for example, that you want to run an efficient key value store in the data center. You'll need to take a few things into consideration. First, low latency is crucial. Applications are going to be bounded by the slowest RPC they can perform, so we want low latency. The key value store itself and the underlying network stack are going to need to be able to handle thousands to tens of thousands of connections per machine on the network. So scalability is also crucial. Finally, both the application writer and the data center operator want the full feature set of TCP. Developers want the convenience of being able to write their applications directly to the sockets interface, and they want the guarantees that their RPCs will come in order and correctly. Data center operators want the flexibility of a software TCP implementation to exchange components like congestion control, and they want strong policy enforcement to ensure that all the hosts on the network get a fair, stable performance. Simplest solution would be to simply go with Linux. Linux provides all these features, but at what cost? If we run a simple experiment modeled after a key value store with 256-byte requests and responses over Linux TCP and a 250-cycle application workload, quickly find we're doing 8,300 cycles per RPC, which means that about 97% of our time is spent doing kernel or packet processing, and only 3% of our time is in the application. So we're only doing a small amount of useful computation. In order to we identify a few key reasons why Linux is slow and has these overheads. First, running the application and kernel on the same core introduces system call and cache pollution overheads. Executing the entire TCP state machine per packet leads to a complicated, inefficient data path. And then because you have to run the entire TCP state machine per packet, you end up with state spread out across multiple cache lines, which leads to poor cache efficiency and unscalability in terms of both server cores and the number of connections that you can handle. So if the bottlenecks are in the operating system, why don't we simply do kernel bypass? We know that the NIC interface is optimized, so we can use hardware I/O virtualization, expose the NIC directly to user space, and use a user space networking stack. By doing so, you get good performance, you avoid the bottlenecks in the operating system, and you get the added benefit of being able to specialize your network stack to match more closely with your application. Problems now are that because you don't have the hard split between user space and kernel, there's no protection between the application and network. So data center operators now need to trust application code to operate correctly and not abuse the network. In addition, by linking your application and network stack directly together, you lose the flexibility to be able to modify or swap out individual components of the network stack like congestion control, which data center operators want to do. Another solution is RDMA. RDMA provides either one-sided or two-sided primitives in hardware to remotely access memory on other hosts directly. And you can implement RPCs and sockets on top of these basic RDMA primitives. By doing these operations in hardware, we can minimize or bypass CPU overheads to do so. However, by offloading part of your protocol to hardware, you lose flexibility to adapt and evolve it, and as well as RDMA is a bad fit for many client-to-many server applications with thousands of connections. There simply isn't enough NIC state to handle it, and RDMA congestion control does not work well at scale. Instead, we propose TAS. TAS is an open-source, drop-in, highly efficient RPC acceleration service. TAS does not require special NIC hardware. It can be run on commodity NICs. It's compatible with all applications that already use sockets, and it operates as a user space operating system service with dedicated cores for packet processing. By doing so, it gets the benefits of kernel bypass approaches with better protection. In general, TAS accelerates TCP packet processing for RPCs with all the desired features. If we revisit these reasons that we identified in Linux for Linux being slow, like application and kernel co-location, executing the entire TCP state machine, and having state in multiple cache lines, we can address these directly in TAS. So we can dedicate cores specifically for network stack processing we can separate our TCP packet processing into a simple fast path and an uncommon slow path, and we can minimize and localize connection state within our simple fast path. In doing so, we get an architecture that looks something like this. The fast path and slow path exist in the same process, with cores dedicated for packet processing, and then applications exist in their own processes with their own core requirements, and all these components are connected by shared memory queues. So once we know that we want to divide up our TCP processing into a fast and slow path, we need to decide how we're going to do it. If we look at what Linux does for packet, Linux does a lot of operations. It does sockets, IP routing, congestion control, acknowledgements, retransmissions, and we want to divide this up into different components. The best solution is to do sockets at the application library level, and then do the absolutely necessary per packet operations in the fast path, like generating data segments, processing and sending acknowledgements, flow control and rate limiting, and then the uncommon or periodic operations in the slow path, so opening and closing connections, running congestion control algorithm like computing the rate, and retransmissions. Then necessary information for all these components can be passed between the shared memory queues. So we can pass raw data packet payloads directly to the application. The application can interact with the slow path to do connection setup and teardown, and control packets and retransmission packets can be forwarded between the fast and slow path. By limiting the operations that we do in the fast path, we then minimize the connection state to only what is absolutely necessary there. So this includes things like sequence and acknowledgement numbers, remote ports and IPs, send rates, congestion statistics. In total, it only adds up to only 2 cache lines of state per connection in the fast path. You may have noticed that I have a few different congestion control operations split between the fast and slow path, so I'd like to talk a little bit more about that in depth. Our congestion control scheme is inspired by the CCP project out of MIT, which proposes running the algorithm in a separate location from where it's actually applied. So what happens is the slow path will periodically check connection state in the fast path and run a congestion control algorithm. Then it will subsequently update the state in the fast path so that when the application sends packets at whatever rate that it wants, the fast path only dequeues and forwards these packets to the network at the specified rate by the slow path. And many congestion control algorithms can be implemented within this framework, and we discuss this more in depth in the paper. But for the purposes of the evaluation in this talk, you can think of DC TCP. Another feature we want to provide is workload proportionality. So as a consequence of splitting up having to divide the CPUs between application and network stack, we need to do this in an intelligent way. So there could be one application, there could be 2 applications taking up as many cores as they need, and they could be receiving or transmitting a lot of packets. So what happens is the slow path will monitor CPU utilization on the fast path to see if it's being inundated with packets. If it is, it can increase the number of cores allocated for the fast path to handle these packets. On the other side, if the applications aren't using the network a lot, and so this fast path CPUs are being underutilized, we can then deallocate them. All right, I'll move into the evaluation. We want to answer a few simple questions. We want to answer what is the throughput, latency, and scalability of our RPCs. We want to know if real-world applications scale with in terms of a number of cores they can run, and if they have low tail latency. And then we want to see if we can distribute throughput fairly amongst all of these connections under network congestion. We compare against 3 other systems, only 2 in this talk. First is Linux, which I've already discussed. The other is IX. IX replaces Linux's network stack with its own optimized data path run in a privileged mode. It uses batching to reduce the overheads of going in and out of this privileged mode at the cost of lower tail latency. IX also does not provide a sockets interface, which means it requires application modification to run, and it also requires kernel modification to support this extra network stack in privileged mode. For our experimental setup, we have an Intel Xeon Platinum with 24 cores, about 200 gigabytes of RAM, and most importantly, we have a 40 gigabit Ethernet NIC that could be considered commodity in a data center environment. Benchmarks we run are a single directional RPC benchmark, an RPC echo server, a scalable key value store, and a congestion throughput fairness experiment under network congestion. All right. First, I want to run a simple single directional benchmark with it just bounded to a single application core to evaluate Linux's and TAS's performance individually. We want to separate out RX and TX, receive and transmit, to see how they perform individually on those sides. We run 32 RPCs per connection in flight and a 250 cycle application workload, and then we vary the message size and measure the throughput on a log scale. What we see is that for a 64-byte RPC, which is like a realistic small RPC, we have a significant performance benefit for TAS. And then at 2 kilobyte packet sizes, TAS achieves the line rate for the NIC, which is the maximum throughput the NIC can provide us, which is 40 gigabits. And it still provides performance benefit over Linux. Some things you might notice are that Linux's performance gets slightly better as packet size increases. This is simply because it's getting more data through per packet processing overhead that it has to do. You may also notice that TAS has relatively even performance across the RX and TX sides, while Linux is slower on the TX side. This can be attributed to Linux doing extra functionality on the TX side per packet, like running the congestion control algorithm, recomputing timers, and stuff like that. The next experiment we want to run is connection scalability. We want to see what's the maximum number of connections these systems can provide. We run a 20-core RPC echo server with a single 64-byte request and response in flight. What we see is that TAS can scale up to about 100,000 connections without any degradation in throughput, whereas IX can scale up to tens of thousands and then begins to drop off with a 20% drop at 50,000 and 2x drop at 64,000. And then Linux has the most poorly managed state and performs slowly across the board. And the key factor here is the minimized connection state. This is about how much connection state you can fit in cache. Okay. The next experiment we run is a scalable key value store. We want to run an increasing number of server cores, but not as many connections as we ran in the previous experiment to give the fairest comparison to IX. So it's about 2,000 connections per core that we run. And we measure just the throughput in millions of operations. What we find is that IX and TAS both provide about 6 times speed up over Linux across all these number of cores. For further clarification, because we're running them on separate, our network stack and application on separate cores, at 16 core case, TAS is running 9 application cores and 7 TAS cores, and IX and Linux are both running 16 app and stack cores. So we want to measure the aggregate TAS cores for this experiment. Another thing is that, as I mentioned before, IX does not provide a sockets interface. So you have to modify the application to use IX, whereas with TAS and Linux, we're running the same unmodified binary. If we instead rewrite our application to use TAS's more low-level interface and forego sockets, we can get another 15 to 20% performance improvement, and we can see that our CPU balance is more on the network side. So we have 8 application cores and 8 TAS cores because we're not doing the sockets overhead on the application side. All right, next we want to measure latency for our key value store. Key value store, so to measure the best possible latency, we run it under low load, which means a single application core and 15% load approximately. And then we want to plot a CDF of the latency for a few different configurations. First, with this purple line, we want to see Linux's server latency with a TAS client, so we can get an idea of just Linux's server latency. We find that to be about 6 times higher at the median. Then, with this middle blue line, we see TAS's server latency with a Linux client to get kind of Linux's client-side latency, which is about 3 times higher. To get a better look at the IX and TAS numbers, I'm going to zoom in a little bit. What we see when we zoom in and get rid of the Linux numbers is that IX still has about a 50% higher latency in the 90th percentile case, about 27% higher latency in the extreme tail case. And if you plot the maximum latency across this entire experiment, X has over 2 times higher maximum latency. And the reason for this, I explained earlier, was batching. So X does this batching to amortize the costs of going in and out of this privilege mode, but at the cost of lower tail latency. Lastly, we run a fairness under incast experiment. What we do here is we saturate the 40 gigabit network card on our server with 4 10 gigabit machines, and then we run an increasing number of flows on the machine to see how task distributes this 40 gigabits among the flows. So we check each individual connection throughput over time and plot the median of that on this graph here. So what we want to see is tasks and Linux being close to a fair share of performance. The fair share line is the green line. In the median case, task adheres very closely to the fair share line. On the other hand, Linux is unstable and fluctuates quite a bit. This is likely due to buffers. There's many different levels of buffering within the Linux kernel, any of which can overflow under network congestion and drop packets. If we go out to the 99th percentile case, so what the connections are getting 99% of the time, we can see that TAS is a little bit lower than the fair share line, but still provides reliable performance, whereas Linux, in the 99th percentile case, is all zeros, which means for all of these connections, at least 1% of the time, they're getting 0 throughput. With that, I'd like to conclude. TAS has the convenience and features of Linux with better performance and stability. TAS achieves this by separating TCP packet processing into a fast and slow path, minimizing connection state, and dedicating cores specifically for packet processing. TAS is a purely software solution that's easy to operate, and I encourage all of you to try it for yourself. Thank you. With that, I'll take questions.
Thank you for finishing on time. Do we have time for questions now?
Hi, Mark Silverstein, Technion. I have 2 small questions. One, do you have any sense how it compares with the user-level stacks like MTCP and all others? And the second question, do you think it's actually feasible to port it into Linux, into mainline? Is it?
Sure. So we actually compare against MTCP in the paper. I encourage you to go look there. There were some bugs that prevented it from being run with some of our experiments, and in general, it actually performed worse than X in all the experiments that we ran it with. Yes, so MTCP was the one user space network stack that we tried pure kernel bypass approach, and it didn't perform as well as X. To your other question, so integrating into the Linux network stack, we'd incur some extra overheads by some relatively small overheads by running our packet processing in the kernel. Just as is, I think it would be very difficult to get it integrated into the Linux kernel. Getting anything integrated into the Linux kernel would be hard. But just running the packet processing in kernel mode is a solution we could explore, yeah.
Hi, Ada Gavrilovska from Georgia Tech. So you combine 3 different things here. You have a different congestion control mechanism, you use sequestered cores for the protocol processing, and then you have optimized fastpath processing. It wasn't clear to me from the evaluation which one of these is really the most critical to the benefits that TAS provides. So can you comment on that?
Yes. So in terms of connection scalability, that comes down to just connection state. Everything else, optimizing our data path, so minimizing the operations that we do in the common data case is going to be a big performance benefit. And then minimizing connection state is also going to be a big performance benefit. I think those are probably equally important. Dedicating cores for packet processing is probably less important than those 2 in terms of performance, raw performance. The other 2, I'd say, probably equal. We don't have any hard numbers on.
I was going to ask, I mean, do you have actual kind of experiments or something that backs this, or this is just your insight?
Actually, yes. Hold on. The benefit of being last is I get to hog the projector.
That's the benefit of being on time.
That too. So what we find is Linux is What we measured is kind of front-end and back-end boundedness, or at least with Linux and TAS. And front-end boundedness is like our instruction cache miss overhead. So that's kind of like something we can fix by simplifying the number of instructions we do. And the back-end boundedness is kind of our cache miss overheads. So Linux is much more bounded by back-end, which means cache misses and data misses. And so we fix that a lot more than the instruction cache overheads.
Yeah, I'll look at the paper then some more.
Okay.
Thank you.
Question here? Question?
Charlie Hu from Purdue University. Quick question, do you have a way, maybe I've missed this, to automatically configure the optimal number of cores dedicated to stack processing?
No, that's something we could look into more. Right now, we just base it on application need. So we increase the number of cores based on what the application needs. In the case where we're running out of cores on the machine, we could try to look into more optimized approaches to balance that. But that's something we haven't explored yet.
Thank you.
Thank you.
Okay, thank you.
So before you go, we have a couple of announcements. So first, the speakers of the first